going to talk about P4 support in ONOS. I'm not sure about the demo. We'll try since I can mirror my screen. Okay, so the agenda. What I want to do today is more of a kind of a little, like tutorial about this P4 support in ONOS. So I'll start giving like an introduction to P4 and P4Runtime. And then I'll talk about more in details how we support P4 in ONOS, like the architecture, the API framework, and the workflow. And if I'm able to see that screen from here, I'll do the demo. If not, anyways. Okay. So about P4, P4Runtime, and P4Info. So P4, as many of you hopefully know, it's an open source domain-specific language for programmable data planes. It's been designed to be protocol independent, so you can parse any headers, new, old, whatever you want. It supports many targets, so ideally you can compile a P4 program into an ASIC, an FPGA, network interface card, or a software-based CPU. And it's designed to be to provide so-called field reconfigurability, meaning that you can add, remove capabilities after switches are deployed. It's based on the well-known match action forwarding model. There are many benefits. There are a lot of papers that talk about the benefits of P4, but what I want to talk about is like the perspective of the ONOS developer. So if you're developing application on ONOS, you're dealing with data planes. And what happens with fixed function data plane is that most of the times, because the capabilities of these data planes cannot be changed, so data plane vendors, they implement very complex pipelines that do everything, but poorly sometimes. Sometimes they do it well. From the ONOS perspective, what we're going to do is stable management, because maybe you want to implement a forwarding application. What we're going to do, maybe is implement a very simple forwarding application, but because the pipeline is so complex, articulated, we end up with code that is hard to write, debug, and manage, so-called spaghetti code, and a very frustrated developer. On the other side, if you have a programmable data plane that is empty, you start by thinking about your simple forwarding application. You write a P4 program that defines the pipeline. You map this you push this pipeline to the data plane, and what happens is that now you're able to, have a very simple application that controls a very simple data pipeline, and so you got code that is easy to read and write, debug, and manage, so-called lasagna code, because it's well layered, abstract, and simpler than the spaghetti code. An happy developer. Okay, now talking about serious stuff, this is the architecture of a programmable switch. What you have at the beginning is a so-called programmable parser, where a programmer declares the header that should be recognized and their order in the packet. Then you have in the middle a programmable match action pipeline, where the programmer defines the table, including the match type, headers, the actions, the size of the table, and the processing algorithm, so like the sequences of table and that should be applied to the packet. Finally, you have a deparser, where the programmer declares how the output packet will look like on the wire. So once you have your P4 program that defines the various block of your pipeline, what you do is you compile it. So you start by asking your switch manufacturer to provide a P4 compiler and a so-called architecture file. So the architecture P4 file is a P4 program that describes the blocks of the pipeline and interface between each block. So you have your P4 program, you compile it, you obtain a so-called target-specific configuration binary. You take that, you load it into data plane, and so what you're doing here is you're instantiating things like tables and external objects, and then in the control plane to populate table entries, and so a packet being forwarded. Today there exists, so this workflow is realized with tools like P4C, the open source P4 compiler, DMV2, which is the open source P4 reference software switch, and P4Runtime, which is the control framework. Let's talk about P4Runtime, because this is what we care about. P4Runtime is a framework for runtime control. It's open source. It was developed by the P4.org API working group, and it's targeted for remote controllers. That's why it uses technologies like protobuf and gRPC. It is P4 program independent. This is very important, meaning that the API doesn't change every time you change the P4 program in the device. So the API is always the same. and enables field reconfigurability, meaning that you have means to push a new P4 program on the device while the device is running. So the architecture is more or less like this. You have a switch that implements a server, in this case a gRPC server that implements a protobuf interface, in this case called P4Runtime Proto, and on top you have ONOS that understands this P4Runtime interface. Just to give an example of the proto file, this is an example of the P4Runtime proto files. It defines messages to interact with the entities defined in the P4 program, like tables, counters, meters, externs, and it also implements defines a bidirectional stream channel that is used for packet ins and packet outs and things like master sheet handling. So if you want to, for example, install a table entry, what you need to do is create a message, protobuf message, where you specify the table ID, list of field matches, where each field match is specified by the ID of the field, where the ID corresponds to the other field in your P4 program, and one of those field match types, like exact, ternary, longest prefix match, depending on how you define the match type in your P4 table. Then you specify the action, in this case, again, specifying the action ID and the parameters, simply using the ID and the value in bytes. As you can see here, for IDs, we use integers. And these integers are used to refer to the P4 entities in the program. The problem is that when we write P4 programs, we use strings. So you write table name, you write an action name, an action parameters name. So how can we get such IDs? This is the workflow of the P4C compiler. There is a file that is produced in the workflow that is called the P4Info. This is the file where we get this mapping between the entity names and the integer IDs. At the end of the workflow, what you get is a target configuration, which is the combination of both the P4Info and the device-specific configuration. Like in the case of DMV2, what you get is a JSON file, which is basically a structural representation of your pipeline in your P4 program. Or if you're running like a Tofino-based switch, what you get is Tofino binary. But the important thing is that the pipeline is defined by both the P4Info and the Tofino binary. Okay, this is an example of P4Info file. In this case, declaring a virtual routing function table where there's an action, it takes a parameter, and in this case, the table matches on 3 other fields, either type, source address, ingress port. So the P4Info generated by the compiler is what you see on the right. So it's basically a description of the table and in the action and the corresponding IDs in the integer form. When it comes to P4Runtime, supposing that I want to install now entries in this table, what I do, I need to create a protobuf message that uses the same ID that I found in the P4Info file. So the bottom line is that to control a P4 device using P4Runtime, you need this P4Info file. Now, what about ONOS? So the challenge here is, or at least the question is, how can we control and configure P4-enabled devices? There's a challenge here because ONOS was initially designed around the OpenFlow fixed function data plane, meaning that the northbound abstractions that you find today in ONOS are morphed around OpenFlow. So you have the same match and action, the same the same capabilities for each table, and also this concept of an immutable pipeline. So the pipeline is there for each device and it cannot be changed. While with P4, you have more generic forwarding abstraction, like for example, arbitrary match and actions, right? And also you have this concept of this mutable pipeline that can change in time for each device. This is an overview of the architecture that you find today in ONOS to support P4 devices. At the bottom, at the protocol layer you have means to use P4Runtime, meaning that there is a gRPC controller that was developed by us and not by the gRPC brigade, that is more for southbound and east-west communication. And we also have a P4Runtime controller and client. At the driver level, we have a default, so-called default driver, P4Runtime, that then can be extended by a device-specific driver, like PMB2 in this case. And then at the core, we have what we call the PI framework, where PI stands for protocol independent, where we have model and we have classes that allows to model PI entities, and we have new services to widen the management and control of these P4-enabled devices. A fundamental element of this architecture is the so-called pipeconf. The pipeconf is a way to pack together everything you need to understand, control, and deploy a P4 program into a device. And pipeconf, the idea is that pipeconf are provided by either third parties or application developers themselves or switch vendors. Once you have the pipeconf, and the pipeconf is registered into the ONOS core, you can control your network either by using what we call pipeline agnostic applications or pipeline aware applications. Pipeline agnostic applications are those applications that program the network using pipeline agnostic APIs, like the flow objective, like intents. In the other case, pipeline aware applications, they use directive flow rules, so they know how the pipeline is structured. In this case, if your application wants to control specific capabilities of your pipeline that you define using P4, now there is two modes of operation for flow rules, which is you can either use the standard match and actions, in other words, the OpenFlow ones, or you can use pipeline-specific ones. I'll give you more details in a second. So about the PI framework, as I said before, it means pipeline independent, but if you want, depending on the context, maybe also protocol or program independent. The important thing is that there's a P at the beginning of each word. So it's basically a bunch of classes, services, and driver behaviors to add in the control of programmable data planes. All these classes start with PI, for example, PI pipeconf, PI table entry, etc. It's modeled around P4 and what is called the portable switch architecture, which is a project in the P4 community to define the minimum set of capabilities of a programmable switch. And it's beta, so if you plan on using this, please don't complain if we change it. As it happened yesterday. In that case, we just removed the whole API. Okay, so a few words about the pipeconf. As I was saying before, it's a way to pack together data and code necessary to let ONOS understand, control, and deploy an arbitrary pipeline. And this is provided to ONOS as an application. It contains the pipeline model, which basically is the description of the pipeline entities. You can see this as a parsed representation of the P4 program. It also contains what we call driver behaviors that are pipeline specific. And the reason is that now you have because the pipeline can change in time in your device. And as you know, there are driver behaviors in ONOS that are used to deal with specific pipelines like the pipeliner. Now these behaviors are not part anymore of the device driver, but they're part of the pipeconf. So each time you load a new pipeconf, that behavior is going to be merged with the driver behaviors. And also the pipeconf contains the target-specific extensions, so which are all those files and information that you need to deploy the P4 program to the device, like for example, the PMB2 JSON, the Tofino binary, and the P4Info. So let's talk about the workflow. So first, once you get your P4 devices, the first thing you want to do is connect that to ONOS. We call this device discovery. So the first thing is registering the pipeconf to the pipeconf service. Once it is registered, because P4Runtime it's based on the RPC paradigm, so client server. In this case, the device implements the server and ONOS the client. It's not like OpenFlow where is the switch that connects to the controller. In this case, the only way to discover the device is by explicitly telling ONOS what's the IP address and port of the device. So what we do is we push netcfg JSON that contains all this information, including also the pipeconf ID. So we're telling ONOS, hey, connect to this device and make sure to deploy this pipeconf. So what happens is that we push this to the general device provider that talks to the pipecom service and uses a bunch of behaviors to both connect to the device and deploy the new P4 program. Once the program has been deployed, what we want to do is perform flow operations. So we want to install flow rules. We start from the case of a pipeline agnostic application, for example, using intents or flow objectives. What happens here is a three-phase translation based on the pipeconf, because we start from the top with a flow objective that needs to be mapped to one or many flow rules. In this case, we use the pipeliner driver behavior that again is provided as part of the pipeconf. Then once you get the flow rule, what you need to do is a translation from the ONOS flow rule to the P4 program specific table entry. And that's because in your P4 program, you might specify a table with certain properties like match type or action. So you want to make sure that the PI table entry is conformant with the P4 table. In this case, the translation happens with what we call a pipeline interpreter that I will explain in details in a bit. And finally, at the P4Runtime client, there's a translation from PI table entries to P4Runtime proto-buff messages, which is based on the P4Info. And that's because of the integer name mapping that I was talking about before. Clearly, if you want to implement an application that takes full advantage of your pipeline, you can bypass the first parts of the flow objective service and the pipeliner, and you can directly write flow rule services you can write flow rules that gets installed bypassing the flow objective part of the architecture. So regarding the interpreter is a new driver behavior that what it does is expose methods to let ONOS understand a given P4 program. Basically, it maps protocol-dependent ONOS constructs to protocol-independent entities. When I say it's a pipeline-specific driver behavior, it means that you, as a P4 program writer, you need to write an implementation of this interpreter if you want your P4 program to work with ONOS. Just to give you an example why we need such an interpreter, take the example of flow rule translation. So you have a flow rule that has match and action. For the match part, what we want to do is, if you're writing your flow rules using a standard ONOS criteria, you need a one-to-one mapping between each ONOS criterion and the header name as defined in the P4 program. For the actions, it's a little bit different because the problem here is that P4 allows only for one action to be executed for each table entry, while on OpenFlow, and that's ONOS, they allow for multiple instructions for each table entry. Take the example of an action that does both header rewrite and forward the packet on a port. In P4, this translates to an action with two parameters. In ONOS, this is represented by two different instructions. So how can we map many actions to one? We need actual implementation logic. That's why we need Java code. That's why we need an interpreter. Finally, the interpreter is also used for other purposes like mapping table IDs and packet IO operations, I will see in a second. Regarding the pipeline-aware flow rules, supposing you won't take full advantage of your pipeline. So for the match part, you can either use ONOS standard criteria, provided mapping via the interpreter. So in this case, you need to provide the implementation of this mapping in the interpreter. Or you can use what we call PI criteria, which is basically a way to define a collection of field matches, of protocol-independent field matches, each one using the P4 header field name, the match type, if it's exact, ternary, longest prefix match, and the value and or mask in bytes form. For the action part, you can either use the ONOS standard instructions, again provided mapping via the interpreter, or you can use what we call a PI instruction. It's a wrapper around basically the name of the action, as in your P4 program, and a collection of action parameters, again using the parameter name and the value in bytes. Want to mention briefly packet IO operation. For packet IO, what I mean is using packet in and packet out, as in the OpenFlow sense. So a packet in is a packet that is received at the switch, it's encapsulated, and it's sent to the controller for further inspection. A packet out, instead, is a packet that is generated at the controller, and then it's forwarded through a specific switch port. Important thing with P4, the encapsulation format, and if you want the behavior that you use to process packet in and packet out, it's part of the P4 program itself. So in this example, you can see this is the header that we use in our sample programs to define the packet in and the packet out. What we do is basically we use one field to carry information like the ingress physical port where we receive the packet, or the egress physical port where we want the packet out to be sent out. For this reason, we need, again, translation, we need to use the interpreter. So this is more or less the architecture in which you have, for example, a packet out coming from an application. In order to send this packet out through a switch, we need to query the pipeline interpreter to see how to construct the packet out header. And then we can query the packet programmable. We can use the packet programmable driver behavior that uses the P4Runtime client that talks to the P4Info. And finally, we send the packet out through the switch. So, try to recap what's the workflow that you need to implement in order to use ONOS to control P4 devices. First of all, well, you need to write a P4 program. And if you want and if you need, for example, things like packet in and packet out, remember that you need to write these behaviors as part of your P4 program. So in this case, you need to write things like the packet in out headers, the actions, the tables necessary to handle that processing. Second, you can compile your P4 program, and then with the compiler output, you can assemble the pipeconf. So first, you create a pipeline model. In this case, in ONOS, you can use directly the BMP2 JSON to generate a pipeline model class. Actually, an instance of the pipeline model class. And then you need to put in the pipeline-specific driver behaviors like the interpreter, the pipeliner only if you need to use flow objective, and finally the target-specific extensions like the P4Info, BMP2 JSON, Tofino. Finally, once you pack the pipeconf, you register this into ONOS, you can finally enjoy your pipeline. And now I would like to show you a demo. Let's see if it works. Given that I can use my screen. Okay, so what I have here, it's ONOS running and minute. So as part of the new ONOS release, we also provide a custom minute script that can be used to run BMP2 inside minute, and also to automatically connect the BMP2 instances to ONOS. So as you can see in the command, we declare this we use this custom script, and we say minute to use a switch BMP2, and very important, we pass as part of the minute command the pipeconf ID. In this case, we're going to use So in this case, we're going to use a pipeconf ID that's called P4 tutorial pipeconf, and we tell minute to control the remote controller to this IP. Okay, let's run the command. So as we can see from the log, as you can't see from the log, so you can see the error messages that I'm showing here because it's too small, it seems the device has been connected to ONOS. I'm not able to show you this because it's hard to type my keyboard looking at the screen, but as part of this minute script, we are generating the JSON that you need to connect the devices to let ONOS discover the device, and this can be found under the temp folder. So here I have my ONOS CLI. What I want to show, the first thing I want to do is to activate. Oh, I can see what I'm writing. Okay, so let's use the GUI. There's no device connected. can I restart ONOS? We have 4 minutes.
We have about 5 minutes.
Okay,
how long it's going to take.
Let's do this. I restart ONOS. We can take some questions if there's questions, and then we try again.
So we're going to try to reboot so we can show you the demo. Does anyone have any questions about the P4 implementation in ONOS and the work that Carmelo's been talking about? As I'm sure a lot of people here know, whenever you mention the word demo and then have an audience, these sorts of things happen.
No questions?
Yeah, can you step up to the microphone up there? Thanks.
Thank you first for your presentation. My question is about the pipeline agnostic application. So as you have several interpretation phase, I don't know if you address the performance problem issue. So because you will interpret several times its pipeline with ONOS, encapsulate that with respect to P4, and this will produce more delay and processing time. So did you look at that?
Yeah, there are definitely some performance issues and exceptions. Okay, it's not the right day for demo. There are definitely performance issues. The way you can solve those is by implementing a cache. So each time, for example, the first time you translate a flow rule to a PI table entry into the counterpart P4Runtime protobuf message, you can cache that such that the second time you need, for example, to remove or install the same, you don't need to translate it again. But in this case, yes, you have at least initial latency to process the flow rule. But at this stage of the work, we haven't looked into ways to solve that problem, to at least optimize the way we do flow rules translation, just to prove that it can work.
Okay, did anyone have another question? No other questions? So in the upcoming ONOS releases, what's next for you and for your brigade?
So what I showed today, it's mostly how we do control, runtime control of P4 devices. Next, we need for sure to work on configuration, and for this, we plan on using GNMI, and that's because that's the let's say recommendation. If you want to say so, it's the recommendation of the P4.org API working group. The idea is to use GNMI, that again is an interface based on gRPC and OBconfig models to provide configuration. When I say configuration, I mean things like reading the status of a port, getting port statistic, LED status, things like that. And then working on new use cases like fabric.p4, in-band network telemetry, and BNF hardware offloading. I see I have 3 minutes, maybe I can try less time.
Give it one more try.
Okay.
Does anyone have another question while we wait for our second reboot? Can you tell it while it's rebooting? Can you tell us a little bit about your brigade and who's working on what?
Okay, so we have many members. Currently we are around 7 members. Most of them are ONF members. We have some community members like Frank from Innsbruck, I don't know, he's here today, and some people from ZTE. I would say we all contribute to similar and different things. So we work the full stack. So we work at the protocol layer to implement P4Runtime capabilities. We work at the PI framework level, where we do also unit testing because those API are used by other applications. We work a lot on debugging not only problems in ONOS, but with the tools we use like DMV2, because these are honestly proof of concepts. Also P4Runtime, it's not a standard, it's an ongoing work, so there's a lot of bugs. Okay, so let's try one last time. Okay, so here my ONOS GUI, ONOS is running. What I'm gonna do, first thing, I'm gonna load a pipeconf. So I'm gonna look for my P4 tutorial pipeconf, this one. let's start the pipeconf. What this pipeconf does is brings in a very simple P4 program where you have basically where I parse only the Ethernet and IP headers. And then there's a table, simple table that matches on 4 fields: English, port, Ethernet, source destination address, and the Ethernet tag. And then we have support for 3 actions like set the address port, send to CPU, and drop. So now that I register my pipeconf, I'm going to start mainnet by specifying this pipeconf ID. Okay, and the device seems to be connected. Let's have a look at the topology. Here's our device. Okay. So the next thing I'm going to do, I'm going to ping the 2 hosts. And the reason why I'm able to ping the 2 hosts is because as part of ONOS, I'm also running some well-known applications. You can see here we have the 2 hosts that pop up. So these applications, if you're familiar with ONOS, are things like proxyr, host location provider, LLDP link provider, and reactive forwarding. These are applications that, when loaded, and especially reactive forwarding, provides basic forwarding capabilities. The important thing is that these applications, they have no knowledge of P4. Here, what we have is all this pipeconf, architecture that translate flow rules. As a very last thing, if you click on the device, you can see, as you do with other devices in ONOS, you can see the installed flow rules. And also you can have a look at the pipeconf. In this case, you can see which headers we're matching on, which actions we're using, the tables that are using our pipeline, and the pipeline-specific behaviors that are exposed by this pipeconf. And this concludes my demo. Thank you.
All right, thank you very much, Carmelo.